Hello, welcome to short lectures in physics. The topic for discussion is X-rays. We have already discussed about the atomic structure and its constituents, according to which matter is composed of atoms, the smallest particle of an element, with a size of about 10 angstrom units. Its subatomic particles are electrons and protons. Electrons are known to be negatively charged, while protons are positively charged particles. The charge for both electron and proton is 1.6 into 10 to the power of minus 19 coulombs, but the signs are opposite. Positive sign for proton, negative sign for electron. The masses of electron and proton are 9.11 into 10 to the power minus 31 kilograms and 1.67 and to 10 to the power minus 27 kilograms respectively. The mass of an atom is known to be concentrated at its center, called nucleus, and the electrons move around the nucleus in circular orbits which are defined in quantized levels. The nucleus contains positive charged particles, protons, and neutral charged particles, neutrons. Mass of proton and neutron is same. This slide shows the central nucleus core containing protons and neutrons, and electrons are moving around the nucleus in circular orbits. According to Bohr's theory, electrons move in definite shells or orbits which are specified with the energy or quantum levels, and they are designated by various quantum numbers. The principal quantum number n is the number of orbit or shell of an electron. The particular orbit or shell of an electron is further subdivided into suborbitals of an electron, which are designated by its azimuthal quantum number L. They are designated as SPDF small letters, for which the azimuthal quantum number L is equal to 0, 1, 2, 3, etc. respectively. The magnetic quantum number denotes the available orbits in a particular subshell. It's like minus L, 0 and plus L. That is for the first orbit, because it is 0, so magnetic quantum number is only 1. For the second subshell it is 3, that means 0 plus minus 1. And for third orbit it is 0 plus minus 2, that is 5, etc. So it is 1, 3, 5, 7 orbits available for different subatomic numbers defined by azimuthal quantum numbers. For each SPDF, the number of suborbital 1, 3, 5, 7, etc. Then each azimuthal orbital quantum numbers, each subshells are allowed to contain only 2 electrons spinning in opposite directions. That is given by spin quantum number S. The value of S is equal to plus half and minus half. Plus half is for the electron rotating in the clockwise direction, minus half is for the electron rotating in the anti-clockwise direction. Here you can see in this slide the various quantum numbers. N is equal to 1, N is equal to 2, N is equal to 3, N is equal to 4. Each shell is designated as K shell, L shell, M shell, N shell, etc. Each shell is allowed to contain number of electrons given by 2n square, where n is the principal quantum number. If n is equal to 1, 2 into 1 square, that is only 2 electrons are permitted in the K shell. Similarly, 8 electrons are permitted in the n is equal to 2, that is L shell. If n is equal to 3, n square is 9 into 2, 18 shells are permitted in the M shell. Similarly, for the n is equal to 4 n shell, 32 electrons. It continues like that. So the number of electrons are subdivided in a principal quantum number of electrons are known, and the subshells according to the different rules, the number of electrons in each subshell is decided. In an atom, electrons in the innermost orbits, that is K shell, are more stable and require very high energy to expel or move them to next higher orbits. whereas it is possible for any electron in an atom's outermost orbit to jump to the next higher energy level orbit through excitation process. Excitation is nothing but making the electron in the lower energy shell to jump to the next higher level by some external source like ultraviolet radiation or visible light radiation. Such an excited electron in a higher energy level orbit will be unstable and hence it returns back to its original state level having less energy. In the process, the de-excited electron, while coming from higher excited level to its ground level, it emits an photon. Transition between various energy levels results in radiations over a wide range of frequencies. The additional energy will be given out by the excited electron in the form of photons. Photons are nothing but tiny energy packets of electromagnetic radiation including light. They are massless, chargeless and travel with speed of light. Energy of the photon emitted will be same as that given out by the de-excited electron. The electron is giving this much energy because of the difference in energies between the excited and original orbits. Frequency or wavelength and hence the color of the light photon emitted is decided by the energy given out by the de-excited electron. It covers a wide range of frequency and wavelength and is called electromagnetic spectrum, in which visible light is a small part. In this slide you can see the entire electromagnetic spectrum covering gamma rays, X-rays, ultraviolet rays, visible light, infrared rays, microwaves, radio waves. The gamma rays have a smaller wavelength, whereas the radio waves have higher wavelength. Because energy is given by EV, the E is the charge of the electron, V is the voltage supplied to the electron, that is EV, potential difference, is equal to h nu. Nu is the frequency, h is the Planck's constant. Nu is equal to C by lambda. So we can calculate if the lambda is known, nu can be calculated, or nu is known, C can be calculated. So different ranges of wavelength and frequency are shown in this slide for entire electromagnetic radiation, the spectrum. So this electromagnetic spectrum is divided into gamma rays, X-rays, ultraviolet rays, visible light, infrared, microwaves and radio. While excitation of an electron from outer shell to an excited state and its return to ground state results in electromagnetic radiation in the visible region with wavelength in the region of 10 to the power of 3 to 10 to the power of 4 angstrom units wavelength. The excitation of an electron from the innermost shell results in electromagnetic radiation in the form of X-rays, for which the wavelength ranges from 10 to the power of -1 to 10 square angstrom units wavelength, that is 0.1 to 100 into 10 to the power of -8 centimeters wavelength. The excitation of neutrons in nuclear levels results in gamma ray radiation. Wilhelm Röntgen in 1895 has discovered the existence of X-rays when he is doing experiments in his X-ray tube. The X-ray tube is a vacuum tube provided with a cathode at one end and an anode at the other end. Cathode is negative connected and anode is connected to positive terminal. A high voltage in the order of 30 to 150 kilovolts is applied across them to generate electrons from cathode and accelerate them towards the anode. In this, a tungsten filament is used as a cathode and it is heated by an electric current that makes electrons get released from the filament due to thermionic effect, that is due to heating. A battery and a low tension AC voltage is used for this purpose. The number of ejected electrons is measured in terms of milliamperes, that is current generated, milliampere units. 1 milliampere is roughly given by 6.24 into 10 to the power 15 electrons generated in a second. The electric current ranges from 5 to 100 milliamperes in the vacuum tube. This slide you can see the Coolidge X-ray tube, also known as X-ray generator, in which a tungsten filament is connected to negative terminal of the AC supply and the anode is connected to the positive terminal. The tungsten filament is the cathode, whereas a high atomic number element like tungsten is used as the anode. Because the electrons are accelerated at a high kinetic energy, lot of heat is generated as they bombard the anode, the tungsten element. So to avoid heat generated, the anode tungsten element in a target material, that is copper block, which is further cooled by a running cold water to an inlet and water out. And the entire Coolidge tube is enclosed in a lead chamber, thus preventing X-rays leaking out of the chamber in unwanted direction. So this is the schematic of the Coolidge tube. So the electrons from heated cathode are made to hit hijacked element with a high kinetic energy that is available by the given high tension voltage. The tungsten, molybdenum or copper are generally used as the anode material. Because of the high kinetic energy, the electrons from the cathode will almost approach the nucleus of the anode target material. As they hit the target and move close to the nucleus, they get decelerated, that means they get slowed down and change their direction of motion. In the process, they lose energy. The loss in energy is emitted as Bremsstrahlung X-ray photon. This results in a continuous spectrum of X-rays known as white radiation. Bremsstrahlung X-ray photon refers to the radiation generated due to stopping or breaking of high energy electrons. Maximum energy lost by the electrons determines the shortest wavelength, that is lambda minimum, obtained in a vacuum tube. Its value can be obtained from E is equal to EB is equal to h nu is equal to hc by lambda, where E is the charge of electron, V is the accelerating voltage, h the Planck's constant, c the velocity of light, nu the frequency, and lambda minimum wavelength of the radiation produced. If V is measured in kilovolts, then wavelength in angstrom units is given by lambda minimum is equal to 12.398 by V. V is the accelerating voltage. Thus, higher the accelerating voltage, shorter will be the minimum wavelength of radiation produced. And the maximum intensity of white radiation may be expected to occur at approximately 1.5 lambda minimum. You can see the variation of the intensity as a function of wavelength in the slide shown shortly. The total intensity of white radiation is approximately proportional to the filament current measured in milliamperes and the atomic number of the anode target material Z and the square of the accelerating voltage, that is V square. About 80% of X-rays generated in the X-ray generator tube is of Bremsstrahlung type, while the rest is the characteristic of the material used as anode. Combination of the characteristic and Bremsstrahlung X-rays will form the entire X-ray spectrum. Bremsstrahlung X-ray region is characterized by a continuous distribution of X-ray beam intensity as a function of its wavelength. It becomes more intense and moves towards lower wavelength or higher frequency values as electrical energy given to X-ray tube is increased, as shown in the figure. Here you can see the X-ray intensity that is measured in the relative units, that is 0.1, 0.2, etc., like up to 1, that refers to 100%, and wavelength in angstrom units ranging from 0 to around 0.5 angstroms also. As the accelerating voltage is increasing, the value of lambda minimum can be seen to be shifted to lower values, as well as the position of maximum intensity also shifts to the lower wavelength regions as the accelerating voltage is increasing. As electrons with high kinetic energy hits target anode material, part of its energy gets transferred to electrons in the innermost shells of the target material. Later they undergo inelastic scattering. As a result, electrons from innermost shells of target will gain energy and gets knocked out of their innermost orbits, thus leaving a hole in the particular orbit from where the electron gets expelled or knocked out. As a result, the electrons from next higher energy level orbits will try to fill these vacancies, holes. In the process, the energy is lost by such electrons in occupying lower energy level orbit that will be emitted as a characteristic X-ray radiation. The characteristic X-rays were discovered by Charles Glover Barkala in 1909. In this slide you can see a high energy electron entering into the atomic structure very close to the nucleus. So the innermost electrons will get hit by the high energy electrons and knocked out of the particular orbit as shown in the dotted electron. That indicates hole created due to expel of the electron from that place. And as the energy is lost by the high energy electron, it will get deviated from its direction of motion by losing energy. Energy lost is spent in expelling the electron from the innermost orbit. So as hole is created, from next higher energy level orbit, another electron will try to occupy the lower orbit. The energy difference is given out as an X-ray photon. So that electron transition from next higher energy level orbit to lower energy orbit results in X-ray photon. In X-ray studies, the transition of electrons from higher to lower energy orbits is described by Shigba notation. If the electron from K shell is expelled out by a high energy electrons from the filament, then K shell there is a hole. This hole can be occupied by electrons from L shell, M shell, N shell which are above the K shell. If the hole is occupied by the electron from L shell, then it is denoted as K alpha emission. If the transition is from M shell to K shell, it is denoted by K beta emission. Similarly, K gamma for transition that occur from N shell to K shell. As it can be easily understood, the energy difference for the K beta emission is greater than that for the K alpha radiation. That is delta E beta is greater than delta E alpha. As energy is inversely proportional to lambda, hence lambda for the K beta line will be lower than wavelength for the K alpha line. So if the transition is from next higher energy level to orbits L shell, it is for K shell, all the series are denoted by K alpha, K beta, K gamma, K delta, etc. If the transition is from next higher energy level orbit to L shell, they are denoted by L alpha, L beta emissions. Similarly, M alpha, M beta emissions and N alpha, N beta emissions. The transitions occurring to M shell or N shell respectively. If you see the distribution of the X-ray radiation, that shows Bremsstrahlung X-ray continuous radiation as well as the characteristic radiation. The K beta line can be seen first at a lower wavelength region as compared to K alpha line at the higher wavelength. Intensity for K alpha will be more than the K beta line. Depending on the potential difference applied to the cathode and anode, the relative intensity increases as the V is increasing. You can see here for V2 greater than V1, intensity of the spectrum at any stage will be more, though the wavelength values at which K beta, K alpha lines appear remain same, but intensities are different. Wavelength of X-rays range from zero point 0.1 to 100 angstrom units. Unlike light, X-rays do not get reflected or refracted. Also, they are invisible to human eye. Being chargeless, they do not get deflected by any electric or magnetic fields also. But they affect the photograph fluids very intensely. They ionise the gas through which they pass, and they are hazardous to human bodies, and they are used in radiography studies. X-rays with wavelength below 1 angstrom unit, that is zero point 0.1 nanometers, nano is 10 to the minus 9 meters, are called hard X-rays. These hard X-rays wavelength region also coincides with the gamma rays radiation, but the origin of their generation is different. Gamma rays are from nuclear level transitions, whereas the X-rays are from atomic level electron transitions. These hard X-rays, they possess very high frequency and energy is also very high, around 5 to 10 kilo electron volts. As a result, their penetrating power is more and they are able to penetrate through large distances. They are generated at a relatively high potential difference, high values of V. They are used in visual imaging, that is radiography, inside of opaque objects, and in crystallography, that is determination of crystal structures of metallic materials. Now, X-rays with wavelength more than 10 angstrom units, that is 1 nanometer, are called soft X-rays. They possess less frequency and hence less energy, less than 1 kilo electron volt. They are produced at relatively low potential difference, low values of V. They get easily absorbed in air. Soft X-ray microscopy is used in investigating properties of nanoscale materials, also used to determine the structure of organic films used in developing solar cells and batteries. They are useful in visualizing internal structures of life science specimens. Possible to non-destructively study biological samples with high resolution 3D imaging, that is better than with electron microscope. Samples studied may include mineralized and soft tissues, organs and organoids, plant tissues, etc. This is known as 3D soft X-ray tomography (XXT). X-rays with intermediate wavelength range of 1 to 10 angstrom units that lie between hard with energy more than 5 kilo electron volts and soft with energy less than 1 kilo electron type of X-rays are called tender X-rays. They are mainly used in synchrotron based X-ray absorption fine structure spectroscopy in life sciences. So these are some of the basics of X-rays and the types and applications and the entire spectrum of X-rays we have discussed. Hope this will give some insight into the X-rays and their applications. See you in the next talk at a later stage. Bye.